Warm welcome back, everyone. This is DB2 Chapter 10, and we continue our discussion of matching queries and indexes. So in the last few videos, we've been talking about composite indexes, concatenated indexes in which multiple columns are present and can be used to support multidimensional predicates. That's a great idea, and also with the nice ideas like partition B plus trees, there's really some benefit to be had. But there are situations where multidimensional predicates occur, but concatenated indexes or composite indexes really cannot help us. And well, these are not exotic situations, as we will see in a minute. These are quite regular queries, and well, we would be faced with the challenge to design indexes that match these particular other types of queries particularly well. And this is what this rather short, I guess, video is about. One such situation. And this situation I'm referring to is disjunctive predicates. So predicates that are using this such or predicates here. Okay, so not particularly exotic. Okay, what we have here is simple scan over table T, but we have to evaluate this disjunctive or based predicate. We are also faced with a multidimensional where predicate here. So it indeed refers to columns C1 and C2 here. Okay. So now our wisdom regarding multidimensional predicates until up to here, it led us to the consideration of composite indexes. But if you think about it, neither this composite index nor this composite index can help us to evaluate the above query. All right, so let's assume we've got this particular index here. Its major column, the prefix of its key is column C1. So what we could do is we could look at this particular part of the multidimensional predicate and try to narrow on an index scan range based on column C1. And well, this index would allow us to do that. But this predicate is symmetrical in the sense that any row T could also qualify regarding its C2 value. So any of these two branches can lead to row T being qualified and being included in the result. So narrowing the scan range based on predicate C1 here is not helping us. Any row that does not qualify regarding column C1 could as well qualify regarding its column C2 and predicate P2. So narrowing on this particular C1 scan range will not help us. If we find that the row cannot qualify regarding this C1, its C1 value, it could as well qualify as regarding its C2 value. So we would have to scan the entire index regarding the C2 values. There is no way that we could narrow down the search using this particular index. And of course, it's the same symmetric situation here on the right hand side. We could narrow down based on the C2 values. Should we find that row T does not qualify regarding its C2 value, it could as well qualify regarding its C1 value. So that means we have to scan the entire index. We would have to scan the entire index for C1 values that make predicate P1 true here. Okay, so instead of scanning an entire index that involves navigating down from the index root, additional I/O and heap page access, as you know, we would then rather access T's heap file directly. Okay, so composite indexes are of no help here in the case of disjunctive predicates. But, well, there's of course something we could do, and it's actually based, the technique that is being used by PostgreSQL and other database systems in this particular case is based on just plain single column indexes. Single column indexes like I1 here and I2, which support the different dimensions C1 and C2 separately. Okay, we would then combine the results of the separate index scans on these I1 and I2 indexes and build the result of the entire query from a combination of the result of these two separate index scans. And the idea that's behind that is actually quite closely related to what the bitmap index scan technique or operator has brought us. Okay, so let's see how that could look like. I think it's already time to switch over to the terminal, so let's do that. All right, so here we go. Okay, so for this experiment, composite indexes are of no value here. We won't use them. So I have, before I came here, I've already dropped them from our index table. Both composite indexes, the AC and the CA index, both are gone. Instead, we are going to use single column indexes, which are anyway rather common. So one of these indexes, this for example, would indeed be the primary key index for our index table. So it would be present there anyway. Index on the C column could be useful in many situations, so maybe we've got it anyway. So that would be the situation, two single column indexes. So let's see whether this is indeed the state of the table. This is table index as you know it, and here are the two single column separate indexes. Okay, so now let's see. We will pose that disjunctive query here using the OR predicate. Okay, this is a query or a range, an index scan range in one dimension, in the C dimension. This is the index scan range in the other dimension, in the A dimension. Exactly the situation that we had on the slides. Okay, so it's time to run that query. Okay, so let's see what happens here. Okay, if we look at the plan here, you see that indeed both indexes, both single column indexes are involved in violation of this particular predicate. Okay, so let's see. Of course, each index is being used to only narrow the scan range on its particular index column. So the index underscore A index is used to narrow down on the A values. This index, the C index, is being used to narrow down on the C values. Okay, that looks good to me. The number of buffer pages that have actually been hit there while we were scanning the index is 13 in this case and 21 in this case. This is a rather narrow scan range, so both indexes have done their job well. These predicates appear to be selective and picky in their own dimensions, and we are benefiting from that by accessing very few pages in each of the both dimensions. So these are two different index scan results, and as you can see, we've been using bitmap index scans in both cases. So what we are left with now is two bitmaps that encode the hits in the C and in the A dimension separately. So you can probably guess what's happened next. Both of these feed their bitmaps into one parent operator, which is of course a BitmapOr operator. Okay, so we use the two bitmaps, we just OR them. So this reflects the logical operator that has been used in the predicate, the disjunctive operator. Okay, this is just a bitmap, a bitwise OR operation as you know it from any of your other studies in computer science. All right, so a bit set in either of the two bitmaps will lead to a bit set in the resulting BitmapOr bitmap. Okay, a row that qualifies regarding one bitmap is good enough to be included in the result. If it should qualify regarding both bitmaps, well, of course, we will include it only once. So there is some automatic deduplication going on here in this case. And there are no further buffers accessed to something. As you can see, we access 21 heap pages, index heap pages in this case, 13 here. That's a sum of 34. This is exactly these 34 pages that the BitmapOr has accessed. So no further buffer accesses here at this point. This is a true bitmap operation. It does not touch further heap pages. Okay, so this will result in a combined bitmap, of course. And this will then be passed on to bitmap heap scan. It's a bitmap heap scan. In this case, the bitmap is small enough that we can even have row level granularity bitmap. This is an exact bitmap, as you can see. So this recheck condition is indeed void. It's not being performed although it's explained in the plan here, that's a pity. But well, we perform a bitmap heap scan, we collect all of our results and present them to the user. So that would be the plan that's been executed here. Very, very nice. A clever combination of two separate indexes in separate dimensions to compute this disjunctive query result. So if you go back to the slides and then switch over to here, you see what we've just seen in the plan and just described is depicted here again. So we implement this BitmapOr, and of course, as you can imagine, we could also implement a bitmap and it's indeed present in PostgreSQL. Okay, so this would also work to support conjunctive multidimensional predicates if we are only presented with single column indexes. So a bitmap and could also support conjunctive multidimensional predicates. So to do that, we would just perform two separate bitmap index scans on the participating dimensions. We could even do these bitmap index scans in parallel. They're completely independent of each other. This is what's happening here in the first step. And what we are left with is page or row level granularity bitmaps, as you know them from our discussion of bitmap index and heap scan. Okay, we would then use this OR operator here in the case of our sample query. This OR operator, this is just the BitmapOr operation that you've just seen in the plan. Okay, and let me narrow down my indicator here. So an indication that we found a hit regarding either of the two bitmaps will lead to a hit in the BitmapOr bitmap. So here there is a hit because we found a hit in this one bitmap. There's no hit here, but that's fine. And there's of course other cases where the first dimension found a hit, the second dimension didn't find a hit, but of course in the result there will be a resulting row. And what we've got here is just a normal bitmap that is fit to be passed to the bitmap heap scan. And that would be exactly what we do here. Of course, the bitmap heap scan will perform a single scan of the underlying file, in table file, in this case it's table T. It has the opportunity to skip some of the pages, as you can see here, and will collect all the results to form the final result. So all of this might sound rather expensive and rather convoluted because there is two bitmap index scans involved and there is this BitmapOr operation involved, and only then we can pass this on to the bitmap heap scan and so on. So all of this sounds rather complicated and costly, but it's a superior alternative to just scan the heap file directly. We can see that if we switch back to the terminal for one more time. And well, force the system to just not use this bitmap scan. Okay, just not use the bitmap scan. And thus disable this technique that we have just discussed. So let's do that just for the sake of this experiment. We would rather not do that in production, of course. And then pose this query again. It's the disjunctive query that we've seen already, and it's the same ranges, index scan ranges in both dimensions. Let's re-execute the query here. Okay, and what we see is a runtime of 1505 milliseconds. Indeed, the system has decided to just use an index scan in this particular case. Okay, and if you recall, we only had a evaluation time of 32 milliseconds in the BitmapOr case. So quite some game to be had here. Well, so all this effort in constructing bitmaps and then using them to combine a bitmap for the resulting bitmap heap scan is indeed worth it. So if it's worth it, let's re-enable the bitmap scan. Perfect. And well, that's it. That's the brief idea, the brief discussion that we would like to have about supporting multidimensional predicates using single column indexes. All right. Stay tuned for more index goodness. We'll see you soon. Bye.